Anybody else in there?
Colton's in there.
So,
Oh, is that?
Good morning, everyone. Am I audible? Yeah. We can wait just a couple minutes for a couple minutes. Someone said yes, thank you. Excuse me. Oh, okay. We can move on. Okay. Well, this is just an introduction to the design projects because from my previous experience, like um, uh, there were some confusion when they wanted to start uh, the whole project. Well, so just to let you know that we are not having any labs anymore. We're done for the semester, and mm, the deadline for submission of this design project is going to be 6th May, 11:59 CST, which has been mentioned. And the software you are going to use here is completely CST and a little bit of MATLAB, which you have done before. The same thing that you have used, MATLAB and also the CST in one of your labs. And I will not take much time today. I will just go through the slides and just will let you know, and maybe I will be ready to take some questions from you, just in case if you have any. However, please note that this is not the only session that I will be having some introduction about or any information about the design project. I will be always open. My room is 205, and I can answer the questions over the email, or you can set up the meetings anytime. Just email me, and we can arrange some meetings. So, and there was some confusion about that lab slot creation, and also the lab because um, because of some limitations or restrictions, we couldn't upload the video for lab 5, which is on the VNA. Unfortunately, um, um, we couldn't do that yet. So if it's still not possible, maybe I will just make that lab 5 submission flexible also for the people who um, couldn't attend the in-person session. And also, as I said, that the lab 7 is gonna be optional also, because you couldn't install the software timely. So because of that, we don't have much slots allotted for lab 7. So we couldn't continue lab 7 anyway. So that's gonna be optional as well. So feel free to ask anything over the chat here, and probably this is gonna be recorded. If there is no technical glitch, let's see what happens, because my Zoom is having, I'm sorry, acting strange today. I don't know why. Hopefully this will be okay. Anyway, so so I'll just go through very quickly. Did not take much time. So yeah, let's start. So this is gonna be at the very beginning, you will be designing a microstrip patch antenna with CST, and then you will be creating a two-element array. You know what array is already, because you've done that when you were designing dipole antennas in one of your labs. Excuse me. And then um, you'll be designing a power divider. Power divider, you'll get to know that pretty soon. I mean, the feeding point, and then feeding point is getting splitted into twos to feed two microstrip patch antenna. So this is this is the array, and the frequency. Well, we have assigned the frequency for each and each. I mean, for each of you guys. Let me show that. Uh, so this is what we have mentioned already. This is gonna be like 3 weeks or more than 3 weeks, 4 weeks, I guess. So well, you don't have to necessarily look into that. It's just step-by-step process, and um, uh, there is something like mentioning about the uh, what do you call this, like parameter analysis. Um, you will get to know that, and let's go there. Okay, let's jump into the frequency selection here. Well, the targeted frequency of the designed antenna would be um, this frequency. Just each of you are assigned with the particular frequency. That means the you target will be, for example, Alexander. I'm not sure, Alexander, if you're designing the antenna, you'll be targeting the frequency of 2.4 gigahertz if you are here, and same applies for everyone else. So so the designed microstrip patch antenna would be working uh, at your assigned frequency. It's I have assigned for the online version students as well, but I have opened the slides for the here, and we have got another one, a separate one, which has been uploaded for the online section. So, do you have any questions about at this point about the frequency assignment, or any doubt over here? Remember, this would be your targeted frequency, and you'll be designing for this particular frequency. For example, Tucker, you'll be designing for 2.52 gigahertz. Remember, the more closer to your frequency, uh, is the system would be better. Okay, and you'll be looking into your S parameter, whether you are going into the right direction. So, do you have any question at this point about this frequency assignment? Okay, so we can go ahead. Well, this is the design requirements. You are going to use the A44 materials, which is substrate height of 8, which is 1.6 millimeter. There's the 4.3, which is the relative permittivity. You know how to assign material in CST, and ground plane material, and the patch is always copper. The copper thickness is going to be 0.017 millimeter. Remember, the copper is going to be copper lossy, okay? Don't use the pure copper. It has to be copper annealed always. So, okay. Now, as we said that we have to design a little bit of MATLAB here because um, let me jump a bit. Let me show the antenna how it looks like. Well, this is the antenna. So this is the microstrip patch antenna. This is the patch, uh, and this is the substrate. And also the bottom layer is ground, and this is the feed line. So just the way we have designed the dipole antenna, the length and also the width. Microstrip patch antenna has to have, the patch has to have particular um, width and length. So, and basically that dimension is completely determining the working frequency of this particular antenna. So since you are targeting for a particular frequency, individual frequency, each of you guys. So in that case, your dimension for your assigned frequency would be different from your peer, from other person. So please keep that in mind. And to set the dimension, um, um, you are using MATLAB. And so let's get back here. So these are the equations you will be using for the initial patch dimension determinations based on your frequency, assigned frequency. So this is the W patch, which is the patch of this, width of the this particular patch. Yeah, I'm having a message here. Oops. Thank you. I'm sorry. What is someone said that the screen is not being shared, but I don't know why it's happening here. Yeah, that's why. Nichols, okay, is there anyone that having the same issues that you are not seeing my screen? Okay. Was it okay just like, a couple of minutes before? Just let me know. Whether I'm just trying to make sure that you didn't miss anything. Thank you. Okay, so moving on. So that's the patch width here, and that's the patch length. So you have got all the equations here. Um, and also the equation of the effective permittivity here. You will be needing that to get your desired width and length. Okay. And so this is for the patch dimension, so we don't need that only here. We also need to measure the correct width of the feed line as well. That will also determine whether the antenna would be operating at the desired frequency or not. So remember, in each and every equations, all the variables would be different from each other because you are working with different frequencies. So each and every frequency will determine what the antenna's dimension should be. And these are the equations for determining the feed line. Just to let you know that feed length is not a big deal here. Rather, feed line is a big deal, and that affects the frequency. So I'm gonna just need to say one thing here, point like, as we mentioned that the MATLAB is just a little part of the whole entire project. So if you just stop at any point, while doing the MATLAB, just let me know. Maybe we can discuss the code. And okay, so you're having the W patch, which is the patch of the patch width, patch of the length, and apply your assigned frequency for initial patch design dimensions, which I already have mentioned. Then you have to measure the transmission line width as well. Remember, the reference frequency is always 50 ohm for the feed line width. So that means you are designing or you are setting the width of the line, feed line, so that it exhibits 50 ohm characteristic impedance. And this is always important to design a perfectly matched antenna. Okay, so, and also I have uploaded a supplementary material, which is called Appendix A. It looks like this, so probably this page would be needing more. And you see the similar kind of equations here. So a little bit of theory here you might want to look into. Okay, so there you go. And just to let you know that also I have set the headline as sample patch antenna design in CST. This is pretty much self-explanatory, very, very detailed explanations. And sample means because probably I have just designed for one particular frequency. So this is, if you just follow these slides, just slide by slide, and it shouldn't be difficult for you. And sample because this is, well, I mean, this is for a particular frequency. So your frequency would not be the same. So please keep that in mind. Don't follow this slide blindly, because this is not necessarily is guiding you to design something that will be working at your frequency. Keep that in mind. And so these things already you know about, some interface about the CST. I'm not going to be spending much time over it. And your frequency range would be 1 to 9. I'm sorry. Yeah. And please, oh, I'm sorry. This is my mistake here. It says the defined frequency range is 1.9 to 3 gigahertz, or maybe you can have 2. Okay. So I don't know why did I set here 1.9. You don't have to do that. Just set your frequency 2 to 3 gigahertz. As long as you target, you assign frequency force into the range, that should be fine. So 2 to 3 gigahertz is a good one. It's a good range. And remember, this antenna is a planar, so don't forget to choose the planar. We are going to work with time domain solver. And also we need this E field and H field monitor. And then we'll start the designing. Definitely we'll be collecting some break from the modeling sections, and you will be needing, just don't put the value straight away into the break or the design dialog box. Rather, you you declare some variable here, so that you can change the value later, and you have to. So you'll be needing that. And once you are initiating some variables other than just putting value, it will look like this. So it's pretty simple. If you, for example, if you don't want this 55, rather maybe you want to have 50, just type it in here, and the whole design will be changed accordingly. It's pretty straightforward. And one important thing is that please save your file, okay? So that you don't lose that and you have to start all over again. Okay. And then Again, nothing is significant here. I see that H is the substrate thickness, which is 1.6, and we are choosing the material FR4 lossy. Please, don't forget that there's so many versions of FR4. So please keep that in mind that you are having FR4 lossy, which is having permittivity, it's like 3.4, if I'm not wrong. Okay. Okay. A very step-by-step explanation. There are some shortcuts that you will get to know here. And I don't see anything different here. It's just the continuation from the previous slide. Okay, that's about the feed line, which is 50 ohm feed line here. Once you're done with the patch and the substrate and also the ground at the very bottom, we're having already we got that initial width from the MATLAB. So put that value in your CST, and that would be your designated antenna. So that is where actually it's pretty much shown with the very instruction based. Remember, just one thing I should say here, the interface that you will be having with your CST. Well, this CST is, I mean, this slice has been made from the when the I mean we have used the CSTs like probably 2015 or maybe 16, I'm not sure. And today is 2025, and also I'm not sure which year you are using in your for your learning edition. So don't get confused. There might be some differences between the within the interfaces and also the instructions, but they're more or less same. And if you're having trouble installation, let me know. Okay. So again, we'll be designing another break here. Which will be our feed line. And there we go. Some detailed instructions here. You can see that aligning, you have to align the coordinate system. Then the other thing that's insert highlighted shapes. So this is pretty much self-explanatory. Shouldn't be a problem for you. And well, so you might have some questions here that like, why are you creating this vacuum or some inset here? Okay, it will look like this. This is a vacuum thing. So, well, I have previously I have shown a picture like this, so that the feed line could have connected straight away with the patch, which is not happening here. Rather, the feed line is sort of getting into the patch a little bit with leaving two vacuum slots at the both side. Well, this is because of the impedance matching, a better impedance matching. Okay, these insets are always used whenever we are designing the microstrip patch antenna, and these vacuum insets or vacuum slots is giving you a very better, I should say it's better impedance matching. So this is the reason that we're using these insets. Impedance matching is all about like, if you are just exciting here, with the waveguide or discrete port. Probably that's the discrete port that we'll be using here. You know, that excitement is happening because of the electricity or current is going through the feed line. So if you are talking about the current or electricity, more specifically, that's the AC current. So in that case, that, you know, it has a question of having a phase. I mean, that is sinusoidal wave thing. So, and that electricity is propagating through this feed line and getting distributed throughout the whole patch. So since we are talking about alternating current, there is a question of phase mismatch. So if you are not having the full wave getting into the patch, that means a portion of the current or electricity will be reflected from this point, and it will propagate backward. So that means you are losing some power or energy or electricity. So this point is really crucial. So actually this portion is providing a little bit of window just in case the electricity is not getting reflected back from this point. At least the patch can avail maximum amount of electricity in phase. Okay, so let's move on. And so as I was talking about the excitation port, you are designing the excitation port, you have done that, which is 50 ohm impedance. And this is going to be a discrete port. Remember, this is not going to be a waveguide port. This is going to be a discrete port. You can still waveguide port, but and you will get the result still, but we are using here the discrete port. Okay. So something about the mesh settings. As I said, that you are not having a lot of options here to play with meshes because that's the learning edition. So you make sure, because this is going to be a very big design. So that means that's not going to be the case right now that we had in our labs, that our meshes were below 100,000. Here, this is not going to be happening. So make sure that you are adjusting the number of meshes by adjusting these values. Okay, just watching for these particular figures so that it falls below or within 100,000. Otherwise, the simulation will not run. Okay, so any question at this point? No question? Okay. Okay, so this is the simulation setup, this default value. You're familiar with these kind of things. Maybe the explanation is too much, but that's good for you anyway. I mean, like, we have used this already in our labs. There's the tolerance, kind of like tolerance or accuracy. Basically, you don't have to play with these things because this is the default value. So that is what I can say, that just don't go for these kind of options. Like, these are already default. And so finally, we got this is parameter, which is just at minus 14 dB, as you can see here. And so it's not the frequency, I'm sorry. There's this parameter, which is minus 14 dB, as long as this is below minus 10 decibel, that should work. And the frequency you can see is probably 0.2, 0.35. So the thing is that, well, this is a good S parameter, but this is not the best, and we can get an improved result. because the lower you can get here from minus 14 decibel is better. And also, for example, if you're targeting targeting for 2.4 gigahertz, or maybe someone is targeting for 2.3 gigahertz. Well, this is not pretty right. Okay, this is somewhere in the middle, 2.3 and 2.4. So to improve the results or any results in CST, there is a feature called parameter sweep. Parameter sweep that you will be, for example, like you see that this is the PL and the patch length. You will choose one parameter, any parameter that you like. It could be patch length, it could be patch width, it could be feed line width. Okay, then you will choose a range. Let's say maybe you will, for example, for this result you got, let's say, for 27, for example. Okay, so maybe somewhere around 27 or 20, maybe 26 will give you a better result. Maybe 28 will give you a better result. Maybe 25.5 or maybe 26.5. But you know. So that means that's not possible. You are not pretty much sure that exactly which parameter will give you the best result or maybe better result. In that case, it's not possible. It's possible. In that case, you have to randomly choose a value and run the simulations again and again, unless or until you are not reaching your sweet point. So, which is let's say 2.4 gigahertz or 2.3 gigahertz. In that case, CST has a feature. You just choose a range, 29, maybe, 26, let's say 26 and 29. You tell it that this will be running at one interval, maybe it could be 0.5, let's say 26, 26.5, 27, 27.5, 8, 8.5, and 29. So there is going to be like 5 to 6 simulations. But you don't have to set that up every time the CS2 is run that for you. And finally, you will get a result like this. So from here, you would choose your best result. And also, it will also tell, for example, this parameter, this red one, it will tell you that for this particular response, the dimension was this. For the green response, the dimension was this. So which one you want? Okay. So this is kind of a like cool feature. But again, you are using learning edition. You might have some restrictions. You might have some limitations. Just one thing I'm telling you, I'm requesting you for sure. Write to me as soon as possible so that we can figure that out. Okay. Don't just wait for the very last moment. that's a request. Okay, so there is all about the parameter sweep. Just I'm not going to be covering details about these things. You see that how they are getting the very, 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 very good result here compared to others. And yeah, okay. For fill pattern, you know how to get that. Remember this button, fill monitor. So go for that. And normally we just choose far field or RCS monitor. You can choose also E field, H field, and far field. So whichever you like, just press apply, set the frequency, press apply, set the frequency, press apply. Okay. Well, again, the similar thing. Oh, sorry, I just went back. Okay, there we go. You're familiar with these things. This is the polar plot. And again, this interface is a little different from the one that we are using right now. So should be all right. Don't get confused here. Now we are moving into the antenna array. So you all you are doing here, you just copy the whole antenna. So remember the distance between two elements or the elements for an array? Well, anyone can answer that, the distance, how much that should be between the element. We have discussed in the class when we were designing the dipole antenna. What distance is the optimized distance? Okay, that's gonna be lambda over 2. So lambda is coming from your sine frequency. So please keep that in mind. However, we are here choosing 0.7 lambda, and that should work as well. Okay. So normally it's going to be 0.5 to below lambda. I mean lambda is too much. So 0.7 lambda should work. Okay. So, well, this is what it looks like. You're just copying the whole things. You are having an empty space since you are copying the one element a little bit away from the previous one you are copying from. So that means you are having a vacant here. Please make sure you're filling this up so that they are all getting aligned to each other. Okay. And oh, this is going to be a 1-2 array. Okay. So you don't have to design more elements, just a 2-element antenna. And for your convenience, if you remember the dipole antenna, when you were designing the array, you had to adjust this simulation settings in the solver setup, and you have to you had to check the both ports. I'm sorry, yeah, port 1, port 2, and there are a little bit of adjustment into the solver setup. Don't forget that. Otherwise, your array will respond as a single element antenna. Okay. So this is how you're improving the results or far field after compared to the single element. You see, this is your target value, which is called directivity. Directivity means this, how directive the antenna is and to a particular direction. So basically the purpose of constructing this array, because array has always an upper hand compared to single element antenna. So this is the original single element antenna, which is just the one microstrip patch antenna. And you can see this is so small, I'm not sure you can see it or not. You see the 6.396 dBi. And after designing the array, quite improved, which is 9.732 dBi. And also the gain will be improved. Right. So this is the finally we reached the final stage. I'm almost done here. This is a power divider. Power divider. So this is a little bit of calculations here. You will start. Okay. This is the power divider. So this is a separate design. Remember, so that means you have to open another CST project, and you will be designing that separately. So here, yeah, these are the steps here. So basically today I am having this session. So one of the most important message that I have to give it to you, that is that because we had some issues in the previous semester, that here you can see the power divider is being designed separately. These are the same thing. I can skip here. It's just like step by step. Basically, you are just Hold on, sorry. Okay. You are having some progression here, and finally, you will bring up something like this. Okay. So this is your power divider. And then you see how the power divider is being copied here into your previous design, which is the two microstrip patch antenna array. So you're just copying the separately designed power divider. You are putting that into your previous two-element antenna array. There are some instructions here. And you see, and finally, you ended up with this design. So I'm telling you that you cannot do that in your learning edition. Your learning edition will not let you copy something, or copy a design, copy any project, and you can integrate that copied design or separate design, I mean, this into previously designed antenna. So that means you have designed the microstrip patch antenna array in a separate project. You have designed the power divider in another project, and you copy the power divider into your microstrip patch antenna array. That sounds more convenient, but actually that's not going to be happening with your CST learning edition. So what my suggestion is that don't open a separate project or separate design or a separate microstrip. Rather, you have your power divider, okay, in the similar project, which is this one. So once you're done, with these things, you'll be just designing the power divider here. Okay. It might be a little confusing here, but it's fine. Just let me know how you were doing with these things. But I didn't receive from everyone that they're having troubles with this. But so I'm not super sure, but you can try. If it happens, because sometimes they just update the features. Sometimes they add features with the software. Sometimes it might be working, so I'm not so sure. So here is my suggestions. Do it the separate design approach. Start with the separate design approach, and then follow these steps. I mean, the integration things. Well, and then try copying the power divider just the way it is shown here. If it is working, that's great. If it's not working, you have to design the whole things in a single project. Just follow the other instructions, those instructions to build up about the dimensions and other things for the power divider. Those are pretty much same, but just you can skip the integration part. This copy and integrate into the previous design. So copy from a separate design and integrate it. Okay. I hope that makes sense. Or if it doesn't make sense, you can just send your confusions here. I mean, or email me. So am I a little bit clear at this point? If I'm not, then let me know. And I think we're almost done. So finally, you are having a design like this. This is a single element. This is a single element. You have done the whole array here, connected them with a power divider. This is a single port. So why are we calling power divider? Because you are having a discrete port here. You are sending the power here, and they are getting split between the two patches here. And you see, again, just like the inset question, remember, I told you that you are having these insets. There could be a reason, which is better impedance matching. You also see here a little thinner portion here, and also little chamfer portion here. This portion is this bended alignment, this cut is not going straight way like this. It's just a little bit of bended. So this is because this is for the, again, a better impedance matching. You are facilitating the electricity so that the electricity can propagate without minimum interference or minimum hindrances or interruptions, and it can reaches to the patch. And also this portion, we call it like quarter wavelength section. This is for better impedance matching. So the length of this portion is the quarter wavelength. That means calculate the lambda over 4. From there, the length you will be getting is the length of this portion for both sides. Okay. And this is the feed line width. This is the feed line width, is going to be the same width. This is the same width. Don't bother about the width here, bother about the length here. Okay. So anyway, this is all illustrated in the presentation slides. Okay, so this is the concern that I have mentioned already, that your CST Learning Edition version might not allow you to copy and integrate the separately designed power divider with your patch array antennas. Remember, I said might not. So please try with your one. You might be able to do that. I'm not so sure. Okay. If you are able to do that, that's great. Otherwise, it has to be designed with a single project. Okay, within the same CST project of microstrip patch array. Just construct the power divider within the same project. Okay, don't design this separately. All right. So I think we are done here. This is what it looks like. Make sure you have achieved the realized gain as greater than 5 decibel, which we have got already. And you are submitting your just CST file, working CST file. And one thing is really important, that name it. Just like this, student ID, and there is an underscore sign, and then frequency number. Frequency number, let's say A, B, or B, or C. C has designed at 2.44 gigahertz, so that has to be C is the student ID, underscore 2.44.cst. And the deadline has to be May 6. If any question or any help, we're here for you. So any question or any concern? You can write here. You can write to me later. And okay, so if we don't have any questions or concerns, maybe we can just start leaving. And I think I'm done with the introduction of the lab project. But if you're not having any questions, you can leave. Thank you. Thank you. Yeah, thanks for letting me know. Thank you very much, Hayden and Nichols. So best of luck with the finals. Thank you very much. I'll see you again.